So we are very, all right. We are very pleased today have Professor Mikhail Stephanov from UIC. He will discuss the hot debated data from experimental measurement, and title is QCD equation of state, critical point, and the dynamics of fluctuation. Okay, Misha, the floor is yours. Please start your presentation. I can see it, but put it into full
Okay,
screen.
let me put it in a full screen. That requires a little bit of sorcery here. Yeah, I know.
On your top left corner, I can see there's a view button.
Yeah,
It needs some Linux magic.
yeah, it needs some Falcon knows. Need Linux magic, exactly. No. Hold on. So what I need is new share. I need to share.
So I don't see any cookies on the table. We run out the cookie money, or oh, there is. Okay, very good.
We hide them from you.
Okay. Okay. Very good. So you are not using computer, you use iPad. Is that the problem, Misha?
No, I'm using Linux. That's a problem. And I need to find the window that I need to share.
Okay.
And I think so. I'm sharing this. Then I'm going to make it into a full screen.
Right. Control L. Can you try that?
Yes, and now I need to share this um, new window. It worked. Oh yeah, new share. Here it is. New share.
True.
You're too fast, Foka.
So what I need is it worked in another Zoom room, but somehow probably this Zoom is configured somewhat differently, so cannot come here.
If you can shrink the left box, we can also start with. That's
We
also fine.
could do that,
Yeah.
yeah.
We talked too much about the first principle. Now we have a practical issue.
Yeah. Okay, so let's then try to simply shrink
Yeah.
the side. Yeah, I think that
Yeah,
should.
it's almost perfect. So,
Yeah, it's almost perfect. Maybe it can be
Good
just
enough.
removed altogether.
Go to view and then get rid of it.
Okay. All right. So
I see you on page 4. And,
yeah.
Okay, so
Now on page 0. Okay,
now
thank
you
you.
have a
Yeah,
title page.
let me see
Go
that
ahead,
it
please. Yeah,
works.
it works. Yeah.
All right, thank you for the invitation, and I would be very happy to share my views on some of the issues and describe somewhat briefly various developments in theory which happened recently and which I contribute discuss with you. Yes, I don't need to introduce the phase diagram or the critical point, the point which separates the crossover from the first order phase transition. At least this is how we envisage a phase diagram. And the conjecture that critical point occurs in the region which can be probed by heavy ion collision motivates the experimental search for the critical point, as well as the theoretical effort, which was and still, I would say, championed by best topical collaboration. First, let me comment, or let me describe the recent slew of theoretical estimates of the position of the critical point. So here is a slide which I borrowed from Manisha's talk, where she assembled the representative figures for these rather different approaches. Let me maybe into the approaches which use lattice calculations, which is basically this upper right corner, the approach by Assar, Hot QCD, Clark et al., and a recent paper by Shah, Vovchenko, et al., where they use different techniques of extrapolating the lattice data, which can be only obtained reliably at zero chemical potential, finite chemical potential, to determine, in the case of Pade, where this singularity occurs in the phase diagram, and that singularity is a critical point, or in the case of Shah et al., they extrapolate the lines of constant specific entropy, and they find that those lines, in the way they extrapolate them, begin to intersect at some point, signaling that function, the entropy versus temperature, is no longer single valued. That signals the coexistence region, or the first order phase transition, the beginning of which is a critical point. The approach, which here is labeled Bayesian holography, or sometimes called by their creators black hole engineering, similarly uses lattice data and extrapolates it to non-zero chemical potential, but this approach is different in that it uses a holographic model, which is, or I would say, a family of holographic model, parametric family, and fixes parameters on zero chemical potential axis as a function of temperature. And then, so it kind of trains this model at zero chemical potential, and then determines where within the range of chosen parameters which fit the lattice data at mu equals 0, the critical point occurs. And so they quote this range, which you see here, 560 to 625. And I think the approach which stands apart from all previous ones, actually, perhaps this is even earlier approach, although this result is recent. It does not use lattice data at all. It's based on the functional renormalization group, or Dyson spherical equation approach. All of them, as you can see, well, there is sort of clarity in the sense that Some of them use lattice data in a different way. For example, these two Padé extrapolations are two different methods. Bazar method is more sophisticated, but all of them seem to place the critical point, albeit with large error bars, in the region between, let's say, 400 and maybe 20 MeV to about 620 MeV. Okay, so this, I would say, is the recent update on the theoretical efforts determine the position of the critical point. And it's interesting to consider it in light of the recent theoretical results, which are also another important milestone in the search for the critical point. The STAR released at CPOD meeting in Berkeley. The data on the fluctuations measured in the B-manager scan. And in order to appreciate the significance of this data, I would like first to recall what we would expect, perhaps somewhat naively, from equilibrium considerations. So what would expectation be if we just look at the equilibrium fluctuation measures, such as cumulants of fluctuations as a function of the square root of S? And the way I would do it is imagine that I focus on the region of the phase diagram around the critical point. This black line is the first of the phase transition, red dot critical point, and the yellow line is the freeze-out trajectory, or the points on the phase diagram where approximately the heavy ion collision freezes out as a function of the square root of S. Increasing square root of S moves this point along the arrow up and to the left on this diagram. And colors indicate the sign of the corresponding cumulant of baryon number fluctuations. So one can, blue sign corresponds to positive, and the deeper the color, the larger is the value of the cumulant. So in particular, one can see that near the critical point, the variance of the second cumulant n equals 2 is enhanced. More interestingly, the high order cumulants also show enhancement near the critical point, actually divergence in the thermodynamic limit. But also their sign depends on the position around the critical point where one measures it. And in the way that I've drawn the typical relative location of the critical point and the freeze out, one can see that the freeze out occurs in the region where the third cumulant is positive, and it increases as we approach the critical point or decrease square root of S. So I try to illustrate it here. So both second and the third cumulant increase towards the critical point, and when we pass the critical point, they decrease. So there is a positive bump in those quantities. The fourth cumulant, contrary to that, first becomes negative and then becomes positive. The origin of this kind of multi-sign structure could be easily understood using the argument which is presented in this review, which we co-authored with Adam, New, Shinichi, and Folka, right? So I have indicated this. These are basically hand drawings of the qualitative behavior as a function of the chemical potential. However, experiments plot this as a function of square root of S, which runs in the opposite direction. So I flip these plots. And this is the summary of what I've just discussed. now with this in mind, we can look at experimental data. So there's clearly a peak in the third cumulant, which is very reminiscent of what we see. And there is clearly a dip in the fourth cumulant, followed by something which one could imagine would become a peak if one continues to low energies. However, this is, of course, not statistically significant. What about the second cumulant? Well, the second cumulant, the predominant feature is this decrease of this cumulant, or the negative contribution to it, which increases as you decrease the square root of s, right? There is a slope. This is understood already before as a baseline, is an effect of, for example, baryon number conservation. So if you take this as a baseline, then one can see that this downward trend towards smaller square root of s is broken at the lower square root of s range. That would be consistent with the positive contribution from critical fluctuations. What is also important to note here, that if we optimistically assume that these are the effects due to the critical point, this statement which we would have to make then is that the critical point is located in the chemical potential bigger than the chemical potential where those signatures are seen. This you can see from any of these pictures. I just focus on n equals 4. You can see that the maximum or the darkest part of the of this structure around the critical point on this freeze-out trajectory occurs at a chemical potential which is less than the chemical potential at which the critical point happens. This would be true for each of these cumulants. And since the last point on this beam energy scan at 7.7 GeV is about 420 MeV, that's the conclusion that we would have to draw from these plots if the signatures, if these features, non-monotonic features, are to be associated with a critical point. However, baseline exists not only for the second cumulant, but also for the third and possibly even for the fourth. For example, the baseline, which was calculated in a paper by Volodya, Folk, and Chun, which takes into account not only baryon number conservation, but also repulsive interaction between the hadrons, produces, well, first of all, it fits very well the data for the second cumulant, except for this bump, which is clearly cannot be fit by monotonic baseline because it breaks the trend. But it fits very well this kind of ramp towards the peak, right? So, and if this were the baseline unrelated to the critical point, then we would have to conclude that the contribution which we need to explain is the negative contribution. That's what Volodya pointed out in his talk last week. Well, similar arguments could be also applied to the fourth cumulant, except that in their model, there is no perceptible baseline in this case. So let's just focus on the third cumulant. So if that is the case, what would be the possible situation or explanation for the negative contribution from the critical point? Well, the one which also Volodya pointed out is clearly the possibility or the scenario in which the critical point is actually below the freeze out. This is the picture which I tried to illustrate. So if the freeze out occurs above the critical point, then this cubic cumulant is negative. And it increases as you approach the critical point. That is just based on the equilibrium expectation. Of course, it has also been known that dynamics plays a role, and in particular, the fluctuations could freeze out effectively at a point which is above the point where the average multiplicity, which determines the average multiplicity, and effectively that would correspond to some memory of the previous evolution of the collision as it expands past this region above the critical point before freezing out somewhere below, while the fluctuation may still be delayed by this evolution. So this is another possible explanation, and that underscores the importance of understanding the dynamical effects of the fluctuations. So these are my comments on the experimental data. Now let me switch to the theoretical framework, which we need to have in order to resolve all these issues and be able to compare the theoretical predictions with experimental data with a goal to connect those observations to QCD phase diagram. So our goal is to translate the information which we can collect into the features of quantitative properties of the QCD phase diagram, in particular, the position of the critical point. And the framework which I'm going to describe is Beeman-Giscard theory collaboration framework, which has been reviewed in those papers which I list here. Basically, it's based on starting with QCD equation of state, which is known from the lattice, extending it in a parametrically flexible way to non-zero chemical potential with a critical point. So we are trying to construct equation of state takes into account all the available information on all about the QCD equation of state, such as the equation of state at zero chemical potential, which is available from a first principle lattice calculation, as well as certain universal properties of the critical point. However, there are properties of the critical point, for example, which are not universal. They can be parametrized. And then what we end up is a parametric family of equation of state, which can be then used in hydrodynamic simulations and then compared with the data. However, since we are comparing to data on the fluctuations, ordinary hydrodynamics is not enough. We also need to know how to evolve fluctuations, in particular non-Gaussian fluctuations. So I will describe this briefly in this talk. And finally, what we also need to do is to know how to freeze out these fluctuations. And I will also describe this in the talk. And I reviewed this in these two contributions recently. Finally, which I will not describe here, once we understand how to connect a given equation of state with given experimentally measurable fluctuations, we can then compare it with experiment, given that what we're doing is essentially solving the inverse problem. We want to determine this multi-parameter of equation of state simultaneously. This seems to be the kind of problem which is designed for either Bayesian analysis or some machine learning or AI techniques. This way, in principle, we should be able to use the data to constrain or even determine the unknown parameters of the QCD equation of state. So let me go through several new developments in this framework, which happened recently. So again, first of all, we need an equation of state, and the first effort in this direction was undertaken by collaboration, best collaboration, and the result is published in this paper, Parotto et al. What this paper did was what I described, and it essentially introduced parameters which describe not only the location of the critical point, but also its other features, in particular the strength and shape of the singularity. So there's a critical temperature, critical chemical potential, mu c. There is angle alpha 1, 2 is a difference. It's basically the angle between the axis. So the way that this equation of state is constructed is that we map the Ising universal equation of state, which is often referred to as Ising equation of state, onto the QCD phase diagram. And this mapping is essentially translates the reduced temperature axis, this R-axis on the phase diagram of Ising model, to some line on the QCD phase diagram. Half of it, of course, is the first of the phase transition. The other half is the crossover, and the axis corresponding to the magnetic field in the Ising model is translated in another line, and the angle between these two lines is alpha 1, 2. Then there is a parameter which we need in order to translate the units of the magnetic field to T and mu or the length of the distance from the critical point on the phase diagram. And similarly for the reduced temperature has to be translated here. These parameters which control these translations are rho and W. Rho describes the relative scaling between the two axes, and W determines the overall scaling and essentially determines the strength of the critical singularity. So these parameters were already introduced in Parotto et al., and the recent development in this direction was reported in this paper by Mikhail and et al., where this equation of state was constructed using a new procedure of essentially resumming Taylor series, which allowed us to be able to construct equation of state which is valid for larger values of the chemical potential, which, as we understand, is important if we want to look for the critical point at, let's say, 500 or 600 MeV chemical potentials. The next development which I would like to discuss is understanding the shape of the trajectories along which a fireball, starting with given initial conditions, expands, and the trajectory which it traces on the QCD phase diagram. These trajectories have very unusual shape. in the vicinity of the critical point, as shown in this plot, which I've taken from this paper by Dora et al. But similar plots can be seen in earlier papers by Nonaka and Asakawa. There is this characteristic cusp, which Dora et al. Call critical lensing, and Nonaka and Asakawa call focusing of the trajectories. It turns out that it is related to the behavior of the specific entropy or entropy per barrier. The reason that specific entropy is important here is because the evolution to first approximation conserves entropy, and therefore, as an expansion, as we know, specific entropy does not change, and therefore the trajectories we are interested in of this adiabatic or entropy conserving expansion are essentially lines of constant specific entropy, which I denote here as hat. And if we want to know how these lines behave near the critical point, it's useful to look at how the specific entropy depends on the distance from the critical point. So at the critical point, the specific entropy becomes a multi-valued function. It has two branches, one corresponding to the phase higher temperature phase and the lower temperature phase. They have different specific entropies. But what is special is that about the critical point is that the behavior of that function is universal near this critical point where these two branches merge in such a way that one branch approaches it from above. It's roughly speaking square root, or more precisely cubic root of the distance of the along the first order line from the critical point. So one branch goes up, one branch goes down, and specific entropy is special because according to the third law of thermodynamics, as you go down in temperature along the first order line, both branches have to go to zero temperature because of the third law of thermodynamics, and therefore that branch where the specific entropy increases has to have a maximum. It's a very simple argument, and it is corroborated by an explicit calculation of the specific entropy in this limit when this maximum occurs close to the critical point. It turns out that for the choice of the parameters of the equation of state, which is used in the to plot this by accident, essentially, used to do this plot, this point is indeed this maximum point is indeed happens very close to the critical point. But the consequences of this maximum are somewhat unusual in the sense that if the expansion occurs along the lines of the constant specific entropy, it means that on this branch, which I called phase one, there are 2 points with the same specific entropy. It means that as the expansion proceeds and the trajectory hits the first order line, it will emerge on the first order line at the same value of specific entropy on the same side. Which side depends on what side is the shows this non-monotonic behavior. It is possible to show that that side is determined by the sign of this thermodynamic derivative, dp by dt at constant baryon density. And if you look at the equation of state, for example, which is used in the best collaboration examples, that side is a Hadron resonance gas side. So in other words, the trajectories look like they're illustrated on the plot on the left. So the trajectory which goes into the critical point so this blue trajectory which hits it near the critical point emerges on the other side. The trajectory is further down the first order phase transition line from here. But those trajectories which hit between the black critical point and the green maximum, they emerge on the same side. So there is this very specific shape of these trajectories, which explains also why this shape, this unusual shape of the trajectories in this plot. So what this means physically is being investigated. We're still not sure how physically that what it actually means. But it's an interesting observation. Okay. So the next development I want to also briefly discuss
Misha,
is
can I just ask you, sorry, can I just interrupt for a second?
yes.
So your derivative dp by dt,
Yes.
that's not universal, is it?
No, it's not.
Right.
It's not.
So
yeah.
that's something we need to know from lattice or from our
Yes.
FRG. That's why I ask them all the time in CPOT, right? I mean, that's what we need to know, right? So
right. That sign, in principle, by extrapolating lattice data, some using Taylor expansion, one
yes.
can determine what it is at approximately this value of the chemical potential, and it's pretty. Well, it's kind of on the boundary. That's why. So the sign changes. When the sign changes, the side which has a maximum flips, and that
Yes.
means that this green point, the maximum, when dp by dt is exactly 0, the maximum occurs exactly here, and then it switches to another side.
Right.
So it is on this picture at least very close to the critical point, but if you look at which side it is on the hadronic side.
Okay.
So that's what, which by the way is also determines whether the reheating occurs or not when you cross the first order phase transition. So the usual picture that we kind of often use is that is the opposite situation where this non-monotonic side is the QGP side. Then you can see that, for example, this blue trajectory hits the first order line and then emerges close to the critical point at high temperature. That's reheating. But this doesn't happen in this scenario.
Exactly.
The trajectories just go down along the first order line, so there is no reheating. The fireball emerges colder than it entered in this coexistence region. But it's a kind of interesting to understand what is the phenomenon happens, right? It's kind of somewhat unusual. Okay. So now, well, this obviously would need to, for that, we need to develop the physics of dynamics of the first order phase transition. But before that, I will not discuss it in this talk. I will discuss the setup or the approach that we are using in order to describe the evolution of fluctuations in hydrodynamics. And this approach is able to treat non-Gaussian fluctuations, which is very important. And its advantage is in the fact that we are able to write equations where we can absorb the cutoff dependence. Remember, you need to regularize those equations because the noise is because they have noise, and this noise is a local noise, like in quantum field theory. Local quantum fluctuations lead to divergences. These divergences can be renormalized away in this deterministic approach. But basically, what emerges at the end, I will just schematically indicate, is hierarchy of equation. The first equation is basically hydrodynamic equation for average quantity psi. Psi brev is a fluctuating quantity, right? Or deviation of a fluctuating quantity from its equilibrium or average value, which is psi. In hydrodynamics is essentially a set, hydrodynamic equations is a set of conservation laws. So conservation laws typically have the form in a given reference frame as a time derivative of the density is proportional to the gradient of a flux. And in hydrodynamics, the flux is determined as a local functional of that density. However, in the fluctuating hydrodynamics or deterministic equations which describe fluctuation hydrodynamics, this flux is also determined by the correlation functions of all orders in principle. Of course, in thermodynamic equilibrium, each of these correlation functions is just a function of this density. So we're back to usual. So the equation closes. But if we are away from equilibrium, each of these correlations of all orders obeys its own equation, which is not conservation equation. They basically relaxes to that thermodynamic equilibrium value. So solving this equation, of course, this hierarchy of equation is impossible without additional observation, which is that small fluctuations are almost Gaussian. And fluctuations in hydrodynamics are small because of the hierarchy of scales on which hydrodynamic is based. There is kind of averaging of local fluctuation reduces their magnitude. And as a result, this equation simplifies. So they essentially become, so the first equation is just the equation which I said of the usual hydrodynamics, which involves only average equilibrium, average quantities and their deviations from equilibrium. The two-point function now base this linear relaxation equation. So it's linear in H, but it relaxes to some function which is non-linear function in psi. So altogether, the system maintains its nonlinearity. So H bar is equilibrium value of H, two-point function. And all subsequent functions have a similar equations where the relaxation happens, it relaxes to a value which is determined by the values of lower order correlation functions. For n equals 2, it's only determined by the average, n equals 1. For arbitrary n is determined on, for example, n equals 3 is determined by the value of average and the two-point function, etc. Of course, these equations are essentially matrix equations because there are several hydrodynamic variables. So this is just a schematic form of these equations. And corrections in the magnitude of fluctuations are essentially the feedback of fluctuations of higher orders. We can be in principle calculated systematically. One can even represent this diagrammatically and see that those corrections are essentially described by loop diagrams. So now before, once we obtain the these hydrodynamic correlations, which I call H or Hn, if it's an endpoint function, which are functions of the n coordinate points in space, usually local, right? Because hydrodynamics is a local description. What we need is then to translate them into observable correlators of particles, right? And those are essentially can be expressed in terms of these correlators of particle distribution in the phase space. So this f is a function of x and p, and there are n's of those f's. So this function is of twice more arguments than the hydrodynamic correlator H. So this procedure essentially for n equals 1 is well known. It's a Cooper-Frye freeze-out. And what we want is the procedure which would generalize this to arbitrary endpoint function. Of course, these correlators of particles are related to, or are the integrals of the momentum space, are constrained by conservation laws to be in terms of the correlators of hydrodynamic variables, which I remind you are conserved densities. However, these conservation law constraints are not sufficient in order to completely determine those functions because it has twice more arguments. There are infinitely many solutions. We know, of course, that for n equals 1, this problem is solved using Cooper-Frye. But what is the generalization? It turns out that generalization is as follows. We find a unique solution if we demand that the entropy of this correlated gas, resonance gas, is maximized. This entropy should be understood not just a function of the particle distribution function f, but also on the correlators of the fluctuations of these particle distributions of all orders Gn. So it turns out that for n equals 1, this is equivalent to the Cooper-Frye. If you maximize the entropy, you will find that the distribution will be either Boltzmann or Fermi-Dirac, depending on statistics. So it maximizes the entropy, a single particle entropy. But if you generalize it to, let's say, n particle entropy, if you wish, or the functional of the correlation functions, then you will get a unique solution which satisfies quite non-trivial checks. In particular, for critical fluctuation, the typical way that the freeze-out was implemented before was to consider a fluctuating sigma field coupled to particles, usually by assumption via their mass. It turns out that procedure reproduces this result of this model, except the coupling is now not just simply to a mass, but by some function of the energy of the particle, which is specified in that solution. And of course, unlike this sigma field model, it applies more generally. While the sigma field model only is able to reproduce the most critical or the most singular contribution to fluctuations from the critical point, this can be used even to describe correlations which are non-critical. And it is model independent. We do not need to assume that some sigma field couples with some model determined coupling. All we need is equation of state of QCD or output of hydrodynamics, and then hydrodynamic correlations are simply related to by kinematic factors, which are determined by the basically resonance gas spectrum, and in particular the particles which are correlated. So capital A, B, and C, this is just example how it looks like for a 3-point function. But it's easy. All other expressions are the same. So capital A, B, and C refer to particles and their momenta, while small a, b, c refer to different hydrodynamic variables, for example, baryon density, energy, momentum density. And so these are the matrices which basically depend on how much, let's say, of a given hydrodynamic quantity, such as baryon number, is carried by a particle of type capital A. And also determined by how many of these particles are. This G bar is essentially the number of particles. This delta hat denotes irreducible particle correlator. It's a correlator which is vanishing for uncorrelated hydrogen gas. but it is more than the difference of a 3-point correlator from the Poisson correlator, because it also vanishes if the gas has only 2 particle correlations, including Bose-Einstein correlations. So it is a, well, Folco will recognize this. This is how one constructs factorial cumulants.
Correct.
So if one neglects Bose-Einstein and Fermi-Dirac correlations, which for protons is a good approximation, these are essentially cumulants, integration of which over phase space with an acceptance produce factorial cumulants. So, right. So this is a very a useful formula because it allows us simply to translate hydrodynamic correlations into observable correlations of any particles, in particular protons. And it allows to express those predictions in terms of the unknown parameters of the equation of state. So here is a very basic application of this procedure to calculate the contribution to the of the protons to, well, of the critical point to the corresponding factorial cumulants, or rather their ratio. This omega k is essentially the ratio of factorial cumulants to the mean. So it's normalized. It's what on my earlier plot of the p-manager scan data was labeled kappa k divided by kappa 1. So this is a first order moment. This is case factorial cumulant. P refers to protons. And one can see what one would expect. There is a bump in the second and the third cumulant. The height of this bump depends on how close the freeze-out trajectory passes below the critical point. So this is a variable delta t here. And it's plotted for one example choice of the critical point parameters. At the critical point at 600 MeV, rho equals 1, W equals 20. And we can also understand semi-quantitatively how this, well, the dependence of delta t is obvious, but we can also understand and plot the results for different values of W and rho, and the amplitude is basically controlled by W, the width is controlled by W times rho in a way which is reasonably well described by these power laws approximately. So obviously, in order to compare with the data so that these parameters could be constrained by the data, we need to do a lot more, right? We need to, in particular, consider non-equilibrium effects, and this is still a work in progress. This is just a very preliminary result.
Yes. Go ahead, finish, and then I ask my question.
Right. So I want to summarize that we are living in an exciting time when the b-manager scan data, phase 2 data is now available, and we can start analyzing it. I would want to point out that there are significant deviations from monotonic baselines in all factorial cumulants, which are at least naively qualitatively consistent with expectation from the critical point. And I want to emphasize that baseline is important for the correct interpretation. I also want to stress that means that if these are the signature of the critical point, and this is still to be confirmed, that critical point has to be at mu b larger than 420 MeV, which coincidentally is in line with recent theory estimates obtained by different approaches. And in order to convert all these qualitative statements to quantitative ones, one needs to do more work, which is underway. Thank you.
Thank you very much, Misha. Very nice. So, Volker, your questions?
Yeah, so previous slide, Misha. So let me see if I understood this. So you take this your equation of state model, which Pareto and al, right? So, and what you plot here essentially are factorial cumulants, right?
Yes, but only critical point contribution to them.
Yeah, so I mean, I would go ahead and take this, do my calculate the cumulants from my thermodynamics, do my whatever linear combination to get the factorial cumulants and be done with this. So what I don't see is how your great development you discussed before enters here.
We are working on that.
So this is just the result if you take your limit to your dynamic model into towards equilibrium. That's sort of your
Yes, if you take equilibrium and you only look at the critical contributions.
Okay, but in order to get this, I don't need your formalism. I could do this the cheap way, right? This result. This equilibrium. Or am I missing something?
I don't think so. I don't think so. What people usually do, because you cannot just take the fluctuations of baryon number and translate it in the fluctuations of the protons.
Oh no, that's fair enough. Okay.
Yeah,
okay.
so that the problem is solved by the maximum entropy. You take the correlate, right? And that gives you a completely parameter-free relationship between the baryon number. By the way, protons carry not only baryon number, they also
No, I got it.
and so the energy fluctuations also enter.
Right. Okay.
Right. Any other questions or comments?
Can I ask a question?
Yeah, go ahead.
Yes.
Please.
Yeah, so in this part of your work, is this easy to consider the kinematic cuts when you do the mapping? Or,
Kinematic cuts?
right.
Yes. Because what we get is a function of, so ABC, each of this index is a composite index. It contains the idea of the particle, like in the, in the resonance gas model, the idea of the particle, and also its momentum, right? So you then, in order to obtain the experimentally measurable cumulant, you have to integrate over that momentum. And in that integration, the kinematic cuts will then enter. So the result
on steroids.
Hmm?
It's Cooper-Frye on steroids.
It's a Cooper-Frye on steroids, yes. So in the Cooper-Frye, you have a function of only one momentum.
Right.
And here you have n moment, as it should be, because it's n-point correlation function.
Okay, so also you need to consider the conservation effect, right?
That conservation is already built in to this formula.
I mean, what I mean is in experimental measurements, you are not measuring the entire system, right? You are measuring the subsystem.
Yes. But the freeze out is local, like in a Cooper-Frye, right? So this maybe I haven't right. So it's the maximum entropy freeze out solution to this problem of determining the endpoint correlators of particles is a maximization of entropy under the conservation law constraints. So whatever hydrodynamics produces will be matched not only on average, as would Cooper-Frye do, but also all correlation functions of all conserved quantities given by hydrodynamics are matched by correlations and fluctuations in the resonance gas by this formula. Am I answering your question? Or I have a feeling that you're asking something else.
Right. I mean, what I mean is like in the work, the non-critical baseline, right, done by Vladimir and Volker and Chen. So they have some kind of correction from the conservation, like considering the fact that in experiments you are not measuring the entire system, I mean, within the entire system, the baryon number is conserved, right? But in experiments, we're not measuring all the baryons from the entire system.
Right.
And you're measuring the mid rapidity.
Right. This is a way, somewhat, I would argue, model-dependent way of taking into account the conservation law. Hydrodynamics doesn't need it. Hydrodynamics is a set of conservation laws. So once you are dealing with hydrodynamics, conservation laws are already included, right?
Yep, but the challenge is what we had to deal with is Cooper-Frye doesn't conserve the particle number, right? So we had to put Volodya's SEM stuff on top of it to ensure the global baryon number conservation is
right. But here you don't need to do it.
Exactly, your stuff does it locally and takes care of it.
It does it locally, takes care of it, and it essentially conserves not only the baryon number, but also the energy density and momentum density, if that is an issue.
Any other questions?
Yeah, maybe one. So Mikhail, how wide in mu b is this critical regime so that you can see some visible memory effects that freeze out?
So far I have discussed, apart from this discussion of the evolution equations, I have not discussed the solutions to these evolution equations. Everything here is in equilibrium, and therefore there is no memory. That said, the width of the signal depends on the choice on the unknown parameters of the critical point. So when we say that we want to find the location of the critical point, this is not the only property of the critical point which distinguishes it from other critical points. Besides location, there is also these parameters rho and w, which determine the shape and the amplitude of the critical point contribution. And of course, the amplitude of the critical point contribution compared to the base contribution, it determines the width of the critical region, right? So the width is another parameter which we would need to determine experimentally. We cannot predict it without knowing the QCD equation of state.
Right, Misha, I have a question about slide 3.
Yes.
And there you separate, you classify these approaches in two classes. One is on the right-hand side. Those are from lattice QCD, and the left implies maybe not. But I remember FRG always compare, in their talk at the beginning, always compare their result of equation of state with lattice. They claim they are same. So fundamental difference in case we use equation of state from lattice comparing to, for example, other calculations such as RG here. So
I had a similar impression, and I asked Jan Pavlovsky whether they use lattice data at all in their calculation. So he claims they don't. However, other people do, because although they say it's a first principle calculation, but they do certain truncation of the infrared effects, which are non-perturbative, in order to write, let's say, gluon propagators, etc. And there are some parameters in there, which I think, as I understood him, some groups use lattice data to make sure those parameters are chosen appropriately. Jan said that they do not use lattice data. They only use it a posteriori to check that their approach produces correct results. Right?
I see. So what you say is there are parameters people could tune in order to match to lattice result.
lattice data. But Jan says that in their calculation, there are no such parameters. I don't really completely understand why
I
he
don't
says that.
understand. Okay.
But he did say that in other approaches, like specifically, that you need some kind of infrared regularization of the gluon propagators, which requires certain parameters which can be tuned by fitting the lattice.
Yeah, but my understanding is they tune these propagators to lattice. They are not tuning towards the lattice cumulants.
Yeah, that's true. Yeah, that's true. They tune to lattice. Yes, they tune to. They do not tune to the phase diagram data. They tune it
that's
to
same thing,
vacuum data.
right?
Yes.
That's the same thing. I think it's in terms of input from lattice.
Yeah, but it's not the same
For
input from lattice.
For example, if we don't have lattice calculation, then
they don't need lattice thermodynamics. They go to the lattice and ask them calculate this gluon propagator for me, and then they tune your model there, whatever the parameters, to get this gluon propagator, and then they do all the thermodynamics, right? So this is slightly different, right?
Yes, that's my understanding too.
They take t equals 0 information and then go from there, right? So this is slightly different.
Yeah. Well, in a sense, the same way as lattice using experiment, right? They choose the mass of the pion from experiment, right?
The needle scale.
So they cannot predict it, right? So, but then,
you want to complete your sentence? Sorry.
Yeah, but then of course, let's say the ratio of masses can be predicted, and something similar is happening here. So to some extent, lattice does find its way into all of these approaches, but to a different degree.
Right.
All right. I don't see any hand, so that's end of the talk. Thank you very much, Misha.
Thank you.
Thank you.
See you soon at other meetings. Yeah.
Yes, I think